Welcome to Akbar Academy, guys. Today we are going to be looking at page 198, the photoelectric effect, and we are going to look at question number 20. So let's get started. The table gives information about two beams of monochromatic light. So we've got beam A, which has an intensity of 6 watts per meter squared, and we've got beam B, which is 0.2 watts per meter squared. Remember, the formula for intensity is power divided by area. We've got two colors here, red light and blue light. Remember, red is roughly 700 nanometers, so it's a longer wavelength than blue light, which is around about 400 nanometers. So each beam is shown in turn onto a barium plate. Beam B causes photoelectric emission, but beam A does not. A student says that this is because the blue beam is more energetic than the red beam. In one sense, the student statement is correct. In another sense, the statement is incorrect. Explain how. This is the biggest confusion between the classical theory of light and basically the quantum theory of light. In other words, light can behave as a particle as well as a wave. So IGCSE, you were always taught about light being a wave. And for much of AS, you're taught about light being a wave because it can reflect, it can refract, it can diffract. But the photoelectric effect doesn't tie in with the classical theory of light. Okay, so why is the student correct? Well, basically, the blue photon has more energy than the red one. So, blue photon has more energy than red photon. Remember, the formula is E equals HF or HC over lambda. And basically, the bigger the wavelength, the smaller the frequency, or the smaller the wavelength, the bigger the frequency. So blue light has a smaller wavelength, therefore a bigger frequency, and energy is proportional to frequency. So the blue photon is more energetic than the red photon. Remember, light is made up of a bundle of photons. But the blue beam carries less energy. Blue beam carries less energy than the red beam. Now, why is this? Well, basically, the intensity of the red beam is 6 watts per meter squared, and the intensity of the blue beam is 0.2 watts per meter squared. So the red one is more intense. Remember, the formula is intensity equals power divided by area. Now, this is the whole point about the classical theory of light, if you don't understand this. Classical theory of light says that if I shine red light onto this barium plate for long enough, I should be able to give it enough energy so the electron escapes. But as we know in the photoelectric effect, this doesn't happen. And this is where the quantum theory of light was born. Next, barium has a work function of 3.98 times 10 to the minus 19. Explain what is meant by the work function. Well, it is the minimum, and minimum is a key word here. Energy required to remove an electron It's a bit untidy. Let me fix that. From the surface of a metal. Okay, and moving on. Then it says calculate the threshold frequency for the barium plate. Now remember, threshold frequency is the minimum frequency that will cause photoelectric emission. So how do we do this? We'll understand that phi equals hf naught. Now this looks really complicated, but basically it's a variation of E equals hf, where phi is the equivalent to E, h is Planck's constant, and f naught, as we call it, is the minimum frequency required to cause photoelectric emission. So f naught equals phi over h, and that gives me 3.98 times 10 to the minus 19 over 6.63 times 10 to the minus 34, which gives me 6 times 10 to the 14 hertz. In other words, this is the minimum frequency that is required to cause photoelectric emission.